Hi, in this session, we are going to introduce an interesting hierarchical clustering algorithm extension called CHAMELEON, which is a graph partitioning on the KNN, means k nearest neighbor graph of the data. So this graph partitioning based approach was developed in 1999 by a group of researchers in University of Minnesota. CHAMELEON actually has some interesting points. It measures the similarity based on a dynamic model. Essentially, two clusters are merged only if the interconnectivity and the closeness between the two clusters are high relative to their internal interconnectivity of the clusters and the closeness of items within the clusters. CHAMELEON is a graph-based two-phase algorithm. In the first phase, it uses a graph partitioning algorithm. Essentially, it clusters objects into a large number of relatively small subclusters, also we call graphlets. Then in the second phase, it uses an agglomerative hierarchical clustering algorithm to find the genuine clusters by repeatedly combining these subclusters or these graphlets. Let's look at the overall framework of CHAMELEON. Suppose we have a large data set. Then we can use KNN graph to merge them into sparse graph like this. What is KNN graph? Essentially, we can assume 2 points P and Q are connected if Q is among the top K closest neighbor of P. Then based on this K nearest neighbor, you construct this graph. Then we will partition this graph into a good number of small subclusters, or called graphlets. Okay. After this partitioning, we are going to merge them into high-quality clusters. How we merge those graphlets back to the bigger clusters? Essentially, the merge is based on these two measures. One we call relative interconnectivity, another we call relative closeness. Relative interconnectivity means the connectivity of C sub 1 and C sub 2 over their respective internal connectivity. Okay. Then the relative closeness is defined as closeness between clusters C sub 1 and C sub 2 over their respective internal closeness. Let's look at the method in some detail. Okay. The first is KNN graph. What is KNN graph? Let's look at the example. Okay. This is the original two-dimensional data sets. So the first nearest neighbor, one nearest neighbor graph is for each point, each object, you just find the top one closest neighbor. For example, this one's closest neighbor could be here, this one's closest neighbor could be here. Then you construct a subgraph based on these. You get a one KNN, you get a one NN, one nearest neighbor graph. For two nearest neighbor graph, is you, for each point you look their top two nearest neighbor, you construct a graph like this. Three nearest neighbor graph is for each point you look at their top three nearest neighbors, then you construct a graph like this. Okay. Then we look at the absolute interconnectivity between C sub I and C sub j. Okay. This absolute interconnectivity is essentially the sum of the weight of the edges that connects vertices in C sub I to vertices in C sub j. Essentially, you look at the weighted sum of these edges. Then the internal connectivity of a cluster C sub I is essentially the size of its mean cut bisector. The weighted sum of these edges partition the graph into two roughly equal parts. Then you look at the weighted sum of the edges of this partition. Then the relative interconnectivity Ri essentially is for C sub I and C sub j is defined by their absolute interconnectivity divided by, or you can say normalized by, the average of their respective interconnectivity. Then we look at the relative closeness and the merge of subclusters. Relative closeness between a pair of clusters C sub I and C sub j is defined as follows. The first is what is absolute closeness between C sub I and C sub j. The absolute closeness essentially is the average weight of the edges connected the vertices between these two classes. Then their internal, essentially the internal closeness, like this internal closeness of C sub I or internal closeness of C sub j, is the average weights of the edges that belong to the mean cut bisector of cluster C sub I and C sub j respectively. That means you look at what is mean cut bisector to cut this cluster or cutting this cluster, then you find their average weights of the edges. Okay. Then you probably can see the relativeness is the absolute closeness normalized with their proportionally defined internal closeness. Then how do we merge subclusters? Essentially, we will only merge those pairs of clusters whose relative interconnectivity and relative closeness are both above some user-specified threshold. That means we only merge those maximizing the function that combines relative interconnectivity and relative closeness. That means even we find those pairs are mergeable, we still want to find these merge, we're maximizing the function. Then, based on the implementation and experiments, we probably can see Chameleon actually can cluster complex objects like this. Okay, this actually these are all the different points with different density, different shapes, as well as lots of noise points. Okay, even with different shapes, different density, and different shapes and different noises, we still can see Chameleon actually generate pretty high quality clusters. Okay, that simply says Chameleon using this graph partitioning and merging methods is pretty robust and generate pretty high quality clusters. Even it is in the spirit of hierarchical clustering, it does do a lot of good with this graph-based method.